When you write code for a single computer, it behaves predictably. Either it works or it doesn't. If there is a hardware fault, like a bad memory chip or a power outage, the consequence is usually a total system failure. The machine crashes, you reboot it, and you move on. The execution environment is binary. But modern applications don't run on a single machine. They run on thousands of servers, packed into massive data centers. At that scale, we no longer operate in a mathematically perfect model. We have to deal with partial failures, situations where some parts of the system are broken in unpredictable ways, while the rest keeps running. The network connecting these machines introduces its own chaos. Packets of data get dropped or stalled randomly. You might send a message and have no idea if it arrived, because the time it takes to travel across the network is entirely non-deterministic. This creates a strict architectural tension. To handle millions of users, you have to distribute your data across multiple machines. But to keep your application functioning correctly, those distributed machines need to constantly agree on what that data actually is. Scaling a system forces engineers into a brutal compromise, guaranteeing perfect data correctness or surviving massive user load. To understand how we navigate that trade-off, we have to look at how data gets corrupted in the first place. Data integrity often depends on how a system manages concurrency, the friction that occurs when multiple users attempt to modify the same record simultaneously. This timeline shows a standard race condition on a used car website. Two users, Alice and Bob, click buy on the exact same car at the exact same time. Buying the car requires two database operations: updating the listing to show the new owner and generating the sales invoice. If their requests intersect, Bob might win the race to update the listing, but Alice might win the race to generate the invoice. The database commits conflicting information from both of them, and Alice gets billed for a car that Bob now owns. This anomaly is called a dirty write. To prevent this, databases use a foundational abstraction, the transaction. A transaction is a logical unit that groups multiple reads and writes together. It enforces a strict boundary. All the operations inside that transaction must execute as one single action. Either the entire sequence succeeds, which we call a commit, or it entirely fails, triggering an abort. Because it is atomic, it ensures that a half-finished process never litters the database with corrupted state. If Alice's invoice fails, her ownership update is rolled back with it. This simplifies error handling immensely. The application code doesn't have to untangle a web of parcel failures. If it receives an abort signal, it simply retries the transaction from the beginning. The transaction acts as a protective shield. It lets developers pretend that concurrency and hardware faults don't exist, safely hiding the messy physical reality of the servers underneath. That protection comes with a heavy penalty. Guaranteeing perfect transaction isolation means the database must process concurrent requests as if they were running sequentially, one after the other. This visualization demonstrates the strongest level, known as serializable isolation. Historically, databases achieved this using two-phase locking, where a transaction must acquire an exclusive lock on a row of data before making any changes. Any other transaction trying to touch that data is forced to wait in line. Under heavy user volume, this creates a severe bottleneck. As the queue of waiting transactions grows, response times degrade exponentially. A single slow transaction can cause the entire system to grind to a halt. Because of this latency penalty, production databases deliberately default to weaker isolation levels to survive heavy traffic. The most common default is read committed. This level ensures you only read data that has been successfully saved, solving basic dirty read issues. But it doesn't stop data from changing while you're in the middle of a larger process. For complex read-heavy workloads, engineers turn to snapshot isolation. This guarantees that a transaction sees a consistent snapshot of the database from the exact moment it started, even if other writes are happening simultaneously. This architectural diagram shows how databases implement snapshot isolation using multi-version concurrency control, or MVCC. Instead of overwriting existing data, the database creates a new time-stamped version of the row every time a value is changed. This elegantly eliminates lock contention. Read queries can seamlessly bypass the write operations by accessing the older time-stamped rows, allowing the system to process massive concurrency without slowing down. But weaker isolation introduces subtle anomalies. A common one is the lost update. This happens when two users simultaneously read a value, modify it, and write it back. One user's write will silently clobber the others, permanently deleting their changes. Even more difficult to track is write skew. This occurs when a transaction reads some data, makes a decision based on it, and writes the result. By the time the write completes, the original data has changed, meaning the premise of the decision is no longer true. Weaker isolation scales beautifully for performance, but it removes the database's protective shield, forcing the application layer to manually guard against subtle, silent data corruption. Even with perfectly tuned isolation levels, a single machine has physical limits. Eventually, no matter how many CPUs or RAM chips you add, the hardware cannot handle the query throughput. The solution is horizontal scaling. You break the massive dataset apart into smaller subsets, called partitions or shards, and spread them across multiple independent machines. This diagram shows key range partitioning, where data is sorted into continuous ranges. For example, all user records starting with A through D go to node 1. Keeping keys in sorted order makes querying sequential data incredibly fast, but this method has a critical vulnerability. If your application suddenly gets a flood of traffic for a specific alphabetical key or a specific timestamp, all the query load hits a single partition. This creates a hotspot, overwhelming one node while the rest of the cluster sits idle. To fix this, engineers use hash partitioning. Instead of sorting by value, the database runs each key through a hash function, which scrambles it and scatters the records uniformly across all available nodes. This ensures an even distribution of data, but it destroys the sorting order. If you need to perform a range query, like looking up a list of users from a specific month, you can't just check one node. You have to scatter the query to every node in the cluster simultaneously and gather the results. If you add secondary indexes to search by other attributes, the complexity multiplies, requiring expensive cross-partition communication just to find a single record. Partitioning is a mandatory strategy for surviving sheer volume, but by physically scattering the data, it destroys the simplicity and efficiency of single-node data retrieval. Once you partition data across multiple machines, you are forced right back into the messy physical reality of networks. Hardware fails, and network links introduce unbounded delays. This creates a complex coordination layer when a single user action involves data residing on two entirely different partitions. To maintain the atomic safety we had on a single machine, we have to use a distributed transaction to coordinate the update across multiple nodes. This network topology illustrates the standard mechanism for this, the two-phase commit protocol. A central coordinator node sends a prepare signal to partition A and partition B, asking if they are ready to commit, and then waits for their acknowledgements. But distributed systems are defined by partial failures. Imagine a network partition severs the connection to partition B right before the final commit command is received. Partition B is unreachable. Because the protocol requires perfect consensus, one stalled node forces the coordinator to abort the entire transaction. It rolls back partition A and returns an error to the user. This is failure amplification. A tiny local fault brings down the whole operation. This exposes a physical limitation described by the CAP theorem. During a network fault, you cannot have both perfect linearizable consistency and total availability. You have to choose one. Synchronous distributed transactions choose strict correctness. They guarantee your data won't corrupt, but their fragility makes them an unacceptable bottleneck for large-scale, high-availability operations. We are caught in an architectural trap. Strict transactions ensure pristine data, but choke under volume. Partitioning handles the volume, but makes strict transactions hopelessly brittle. To escape this, modern data systems abandon synchronous, lockstep coordination. Instead of forcing every node to agree before a write succeeds, they decouple the components. This diagram illustrates a decoupled data flow architecture. User actions are simply appended to an immutable event log. That log then asynchronously pushes data through a stream processor, which processes the events to update separate read views. Data integrity is maintained not by global locks, but through stream processing. By designing operations to be idempotent, meaning they can be applied multiple times without changing the result beyond the initial application, the processor can safely catch duplicated network messages. It suppresses the duplicates, ensuring the read view updates correctly exactly once. No single tool solves every data challenge. Designing a system is a process of selecting specific trade-offs, ensuring that the system's faults and limitations align with the actual requirements